Let me start by thanking the organizers for including this paper in the program. It's an honor to be here, part of you guys celebrating the memory of Zvi Griliches. The paper I'm presenting here is joint with Martin, who's here, as well as Giuseppe Berlingieri from ESSEC and Rigo from LSE. And me being based at the New York Fed, the usual disclaimer about the Fed applies. Now, for this crowd at least, it should not sound like an exaggeration if I say that the new Schumpeterian theories of creative destruction have brought about a revival of sorts in growth theory. And they've done so by linking economic growth to the firm-level innovation and growth. And in doing so, they have allowed us to use the richness of all the microdata we have available on firm growth to think about the drivers of aggregate productivity growth. Now, of course, firms can grow in multiple different margins. The focus of these theories is on the margin of product innovation, the way in which firms come up with new products. In doing so, they create knowledge spillovers for others, but they also replace old products, and in so doing, they steal business and create negative externalities. So the richness of these positives and negative externalities distinguishes these theories. Yet we know that this is not the only way in which firm growth happens. Firm growth also happens by firms trying to raise the revenue on their existing set of products, and perhaps they do so by investing in process innovation. And perhaps there are also differences between externalities that we observe in product and process innovation. For this reason, we would want to basically make this distinction clear. Now, there's been a lot of work, there's been a lot of progress over the past couple of decades in this area. A lot of you in this room have contributed to this literature. One of the key limitations, however, has been that because of the limitations of the data, the fact is that the data most of the time tells us what the revenue of the firm is in totality. We don't get to really use the data to investigate product dynamics. Most of the heavy lifting for understanding where the creative destruction lies happens through the structure of the model, not directly through the data. And our job in this paper is to bring about data that confronts and disciplines these theories directly with observations of product-level data on firm growth. The quick review of outline of what you're going to see today, the data is coming from French manufacturing firms. We're going to use this to document a number of stylized facts that we think go to the core working of these models. The first one being that product innovation is a highly concentrated phenomenon. There are some superstar product innovators that the small share of them that contributes disproportionately to the number of new products every year we observe in the data. We also show you that this concentration of product innovation is very important for understanding product production concentration in the cross-section of firms. And we also look at what we think is an important connection between product innovation and process innovation by looking at the life cycle of revenue growth of continuing products, showing you that, in fact, the immediate years after a product creation is where most of the action in terms of revenue growth of the firms are happening. We're going to show you a very simple extension of the workhorse models of creative destruction with this idea of innovation burst that allows us to fit these facts in the data, and we use the model in the context of a simple calibration to study the contribution of creative destruction to objects that in the aggregate we care about, like productivity growth or the concentration of production. Okay, so let me jump right away, given the time constraints that have been emphasized here, right into the empirical analysis, starting with the data. So the data is EAP. Some of you have already used this in some other applications. The data is telling us for each French manufacturing firm the composition of the quantity produced and the sales of the firm at the level of around 4,000, roughly 4,000 10-digit product codes. The data is comprehensive of all the firms with more than 20 employees, or roughly 5 million euros in revenue, and covers 90% of production in French manufacturing. We have 10 years of start data starting in 2010. Of course, the main assumption we're going to make is that the notion of a product code in this data corresponds roughly to some notion of product blueprints in these theories of creative destruction. And doing so, then it's very obvious what we have to do. We're going to take the portfolio of the product of the firm to be the set of those product codes in which the firm sells non-zero values. Okay, so now before jumping into the firm growth and product innovation, I want to use this data to revisit some very basic fact about firm heterogeneity. That's been one of the most robustly documented facts about firm heterogeneity is that there's a high concentration of production. In our data, top 20% of firms roughly are responsible for 80% of revenue and employment in the cross-section. And typically the way we think about this concentration is this idea of parallel tail behavior, meaning that there is a linear relationship between the firm size and the rank in the distribution, both when they're both expressed in log terms. So let's look at this. Using our data, we can look at this in terms of the number of products. And this is what we find. So on the x-axis, I'm showing you the number of the products that the firms have. On the y-axis, the rank of the firm, and both of them are in logarithmic scale. And what do we find? Voila, we have this really neat linear relationship, meaning that a small share of the superstar firms basically sell the disproportionately large share of the products that are present in the market. So this number of products is an important margin for explaining the concentration of product in revenue terms. Okay, so now let's use our data to start with the variable that perhaps is the most important, the most crucial in these theories of creative destruction, which is the rate of creative destruction. So what am I showing you here? On the first column to the left, I'm using our data. So this rate, typically when we are disciplining our models, has to be inferred indirectly based on fitting the data to, let's say, the rates of productivity growth. But here, I can actually read it off in the data. So the first row is telling me what that rate is for a typical firm, the rate in which it introduces a new product. The second row is the rate at which it loses a product. The rate is roughly 7 to 8%, a little bit higher for destruction, product destruction. Why? Because part of this destruction is happening by entrance that is not showing up on the first row. Okay, so this is the first order fact. Now, what I want you to pay attention to is the remainder of the columns. This is looking at the same rate conditional on the firm's current number of products. And here, there are some differences, but there's no clear trend in terms of the number of products that the firm has and the rates of product creation and destruction. Why is this important? This is one of the key underlying assumptions of the theory of creative destruction. Partly it explains the Gibroth law, although Timo, as we saw today, gave us some reason to perhaps question that assumption. But it also is really important for the tractability of these models. Without this assumption, with these assumptions, it's going to be much harder to be able to work with these models. And so to our knowledge, this has not directly been tested before, and we are basically showing you evidence that, in fact, there isn't clear-cut evidence against it. It seems like the data is compatible with this assumption of these models. But these are all averages, right? Let's now look at heterogeneity. What I'm showing you here on the x-axis is the number of new products of the firm. On the y-axis, again, the rank, the same way to show you the distribution, both in log scales. And this is conditioned on the firm in the past period having only one single product. So this is essentially the rate of product innovation for firms with one product. What do we find? Once again, this linear relationship. There's a fat tail of superstar product innovators that, again, give us a disproportionately large share of all of the new products in the market. And this is going to be one fact that the standard models, given the process of product innovation that they assume, are going to be having a hard time fitting in the data. Now, you might ask me, well, how do we know that these products with the right tail are actually coming from these superstar product innovators? Maybe these are firms that are very creative in labeling their products. They're going to basically come up with one idea and then label it as if it has been in multiple different product codes. What I'm showing you here, for the same data, same set of firms, on the x-axis, again, number of products, on the y-axis, the average revenue per new product. If that were to be the case, it has to be that these firms that are giving us all of a sudden a lot of products, some of these firms have one product in the previous period, now all of a sudden they have 20, 30 new products. They have to be earning less revenue per new product. And this is indeed not the case. What we're finding is that these products are roughly comparable across them. So this is one, and we can do this, of course, also the previous slide, we can look at show you all of these at the level of firms that have different numbers, product, 5, 10, 20. We do a whole lot of robustness checks on this fact. We look at alternative definitions of products when we use more aggregate definitions instead of 10-digit at 8 and 6-digit. This pattern seems to be fairly similar between old and young firms. The fact that the firm may or may not have recently engaged in product innovation does not change the tail behavior substantially, and it also appears to be fairly widespread across subsectors of manufacturing. Okay, so now let's move on to use our data to investigate the contribution of creative destruction to firm growth. So what I'm doing here on the left-hand side, this is the standard Steve Davis, John Haltiwanger, and co-authors way of thinking about revenue growth. And in the numerator, I have the change in the revenue growth of the firm. In the denominator, it's the average of the past and current revenue. I can write this in as a sum of three terms. The contribution of revenue coming from new products, revenue lost due to product destruction, and revenue growth in the set of continuing products. So perhaps this last term is somewhat connected to process innovation, but the two other ones are tightly linked to creative destruction. And what I'm going to do is that for each of these terms, I can look at the Shapley-Owen marginal contribution to explaining the R-squared on the left-hand side. Okay, so first row is showing you how, on average, these three terms look like over a window of 1 year. Main message is that the majority of the variation in firm growth is explained through product creation and product destruction, roughly 70% of it. And of course, as you increase the window, almost mechanically, this number is just going to keep increasing because there is more space for product creation and destruction. Okay, so this is an average. But let's now look at the way in which this contribution unfolds across different points in the distribution of firm growth. So the figure on the top is inspired by the nice paper by Petrus here and Daniel Garcia-Macian and Chang-Tai Shea. What it shows you is that it's looking at each bin of firm growth. Again, in the same way that we just looked at, it runs between -2 and 2. And it tells you for each bin of size, to the right, the contribution of that bin of firm growth to the aggregate growth of growing firms, and to the left, the contribution to the aggregate decline of shrinking firms. So what do we find here? We find that this is something that we have in France. They had it in the US with employment data. We find that the majority of the change, a good chunk of the change, is coming from firms that have experienced moderate rates of growth or decline. Roughly the numbers between -1 and 1. Yet there is still a lot of action in the extreme tails. And these are firms that a lot of them are entering and exiting. You cannot ignore that for understanding growth. Now this is the picture you get if you have only firm level data. Given our data, we can look under the hood of this figure. So underneath this, what we're doing is that for each bin of firm growth, I can do the same decomposition. I can tell you how much of the variation there in growth is coming from either creative destruction in green or continuing products in gray. And the fact I want you to notice here is that as we go toward the tail of firm growth, that's where creative destruction is playing a larger and larger role. It's increasingly becoming more important. At the very extreme, of course, by construction, firms that are entering and exiting, that's all creative destruction for you, right? So again, the important thing is that if we want to think about the implications of these different externalities and the difference between product and process innovation, our quantitative models, we think, should fit these facts that we see in the data. And then finally, the last fact that I want to emphasize is this fact. So we're looking at the process innovation, or basically the indication of that in our data, which is revenue growth for continuing products, as a function of the year since the product was introduced. What do we find? The largest rate of growth of revenue is happening immediately after creative destruction. In a sense, it's as if not only is creative destruction is giving us this improvement, initial improvement, it's expanding the range of feasible spaces that the firm has for process innovation. And then increasingly since then, this rate declines. So in the remaining time I have, I'm going to walk you very briefly about the structure of the model. I'm not going to get into the details because for the most part, we have a standard structure. The households are very standard. The same CS aggregator as usual. Firms have quality differences in the products they sell in the market. simplifying assumptions that markups are constant for the firm that has the highest quality within each product blueprint. The key part is our description of the drivers of firm growth. On the side of product innovation, in the next slide, I'm going to tell you we have this notion of innovation burst that's going to allow us to explain the concentration of product innovation. On the side of process innovation, we have this idea of decreasing returns to process innovation. As more and more process innovation happens on the same product line for the same firm, it becomes increasingly harder for you to come up with new ideas in terms of improving your process. And to fit the data that I showed you in the previous slide, we need to include also some quality shocks. Entry and exit is standard. So what is this notion of innovation burst? When a successful innovation happens in the standard model, you get one product. Here, you have a potential burst, and the number of these products that you're going to get is characterized by this zeta distribution. Theta is the key parameter that tells us the degree of concentration. If theta is infinity, you're going to get exactly the standard model where each instance of product innovation brings about one product. But here we have this degree of freedom that allows us to fit the concentration. Now, as usual, each product that comes into the market potentially brings about this improvement eta. And on the side of process innovation, similarly, we have this potential improvement lambda on your current product, except that here we assume that these quality improvements have the decreasing returns as they accumulate over time. So otherwise, the model is fairly standard, and yet it remains tractable in all the ways that we know and love about the functioning of this model. So let me just use the remaining time I have to show you how well this simple extension allows us to fit the facts in the data. To the left, I'm showing you the data on the distribution of new products. For one product, we can calibrate this model very simply. I'm going to spare you of the details, directly fitting the parameters to the moments in the data. For instance, the theta parameter is basically fit exactly to this slope. And on the right, I'm showing you what our data gives us, which lines up with this. The red dot is basically going back to the standard model and trying to calibrate that model with otherwise exactly the same data, with the exception of binding the hand of this model with theta being infinity. And as you can see, it has a very hard time giving rise to these stellar innovators, product innovators. So we calibrated with one product firms. Now 10 product firms, once again, we do a good job of fitting it, whereas the standard model fails. And again, this is unconditionally the same issue. Now, going to the cross-section now, what I want to show you is that once I fit this distribution of product innovation, all of a sudden we can do something that is very hard for these models to do, to fit the cross-sectional concentration in production observing data. And then finally, one important exercise I want to show you is how this model is going to allow us to think about the contribution of creative destruction to growth. So what is growth here? It's eta, improvement due to creative destruction on average, tau, the rate of creative destruction. Lambda, improvement due to process innovation, tau p, the rate of process innovation. So the simplest way to think about the contribution of creative destruction is just to look at the first term, the share of the total growth explained by the first term. The underlying idea here is that process innovation is fixed. It's not changing due to any changes in creative destruction. The next idea is let's completely drop growth due to creative destruction and see what happens. And then finally, I can think about the marginal effect, but adding in the potential consequences of a marginal change in rate of creative destruction on process innovation. That can happen due to two potential forces in our model because of the fact that this life cycle distribution matters. As the rate of creative destruction goes up, we now all of a sudden have tons of young products. And these young products, as we've seen, have better potential for process innovation. But so this is a positive impact. The last impact is the standard one. The discount rate of firms goes up because they know that their products are more likely to be displaced, so they have less incentive. So I'm going to show you this one table that is basically summarizing. The first row is this first exercise. This leftmost column is our model. The middle column is, again, a model a plain vanilla model, let's say Clary-Corton, with only product innovation. The last one is a model that is more sophisticated, includes process innovation, but without these decreasing returns. So what is the share? What we find is 15%, which roughly lines up with a model with a model that allows for process innovation. Of course, a model that has no process innovation would say that all of growth is coming from creative destruction, which might be a little bit in a way counterfactual given the data I've already shown you. What if I completely kill creative destruction? Now, all of a sudden, our model responds similarly to that plain vanilla model. Why? Because in our model, if you kill creative destruction, the space of feasible process innovations will diminish over time, and ultimately the sustainable growth ceases to exist. So all of a sudden, we give you a response that looks more like claricortum, and then this marginal exercise, the number we find is higher, is 25%, 10% higher, and this is a sum of two terms. Remember, there's a discounting effect. This discounting effect you can see in the last column. It's substantially negative if you don't allow for these decreasing returns. Whereas once we allow for the fact that this rise in the rate of creative destruction is bringing about younger products, all of a sudden we get a kick out of that is even higher than the negative discounting effect. So there's, in the paper we look at also consequences for concentration, and we think that's also another really interesting margin here. I'm going to leave it here for, to hear the points that our discussant is going to make. Thank you so much.
Thank you. Thank you.
So thanks a lot for inviting me to discuss this super nice paper. It was really a pleasure to read it. Let me give you my one-slide overview. So as Danial said, there's been a burst of research into creative destruction since Philippe's foundational work. And in those models, a key source of growth is basically continued product improvement. Okay. What this paper is asking is a very simple question. What does that process look like in the data? What does product improvement look like if we can measure it? So if you want to put it in even broader terms, what we're doing here is we're really kind of following the Griliches program of let's start with measurement first and then also try to measure things at the micro level where economic decisions are made. So here we're kind of opening up the boundaries of the firm and we're looking within firm at products. Okay. So their main contribution is to leverage this amazing French data on product, well, it's data on a lot of things, but one of the things is data on their product portfolio. I'm going to use the word product portfolio today because I guess I'm in the finance department and we think about portfolios all the time. So what are the key findings? There's a lot of empirical stylized facts here. I'll highlight a few. I'm not going to have time to talk about all, but the size distribution of product portfolios has a fat tail in the data. Not only that, but firms add products to their portfolio in what the paper calls bursts of innovation that also themselves have fat tails. And then when you embed this feature of the data, the fat tails and the bursts of innovation into a relatively standard quality ladder models, you can get a much bigger effect of creative destruction on productivity growth. And you also do a better job at fitting key facts about the cross-sectional distribution of firm size and concentration. So I want to give a couple thoughts on the data, which I think is fantastic, and then also my sort of naive reading of the model. The data first. So what we're doing here is we're taking firm J near T. We're looking at the number of products that this firm has positive revenue for, and we're also computing something like the gross change in the number of products from T minus 1 to T. So this is the products that you didn't used to have positive revenue for last year, but now you do have positive revenue for. And then I sort of already highlighted some of these facts. Power law in the number of products, power law in the gross rate of change in the number of products, and then the churn, this kind of continuous change in the set of products the firm produces, contributing substantially to aggregate revenue growth. So this is one of the many beautiful graphs in this paper. On the horizontal axis, you have the size of that increment in the product portfolio. On the vertical axis, you have the ranks of firms, and you have a beautiful log-log rank plot. So here's kind of a small digression, but this is to tell you that this data is very rich and it actually puts a lot more constraints on the types of models that we can write in a way that I think is super nice. So here's some very simple, this is just a statistical decomposition. Think about the conditional gross number of products you add on average. This is conditional on your initial size. That has to be equal to the probability that you add at least one product, let me call that the innovation rate, times the expectation of the number of products conditional on having innovated, okay? So one of the things they're telling us is that the distribution that lives inside this expectation here has fat tails, okay? So that's the bursts that they're talking about. But they're actually telling us more than that. So one of the things they're also telling us is that this doesn't really depend on size. It looks pretty much the same regardless of how many products firms currently have. And then they're telling us a third beautiful thing, which Danial showed, which is the product innovation rate is independent of size. So what is the product innovation rate? It's the thing I wrote there divided by the initial size of the product portfolio. And so just, dividing through, you can see that basically, since we know that this guy is independent of size, down here, this ratio here has to be independent of size. And this ratio is what we call in quality ladder models innovation intensity. So it's the rate of arrival of new things divided by the number of existing things. The fact that so the data basically is forcing us, since this is independent of size, this is this table here, and this as well, this is forcing us to write models where this is independent of size, and that's precisely the assumption we make very often. So I think that's fantastic. Now, I think we do have to sort of take one little step back and ask, well, what is the product in this data and what are we measuring exactly? So here's an example. I pulled this up from the European Commission's listing of these product codes. This is extremely boring. It's the manufacturer of plastic packing goods. So let's focus for a second on the stuff at the bottom here. So this is a six-digit. So they're using a more refined classification, which is 10-digit, but this is the 6-digit level. Carboys. What the hell are carboys? I was wondering. I'm not a, English is my second language. This is a carboy. Okay. Okay. So this thing. Okay. So at the 8-digit level, this classification is distinguishing between less than 2 liters and more than 2 liters. Okay. So it's very, it's a pretty refined distinction. We do have to ask the question of, in our models, we would like these products to capture the things that are not really substitutable. That is the spirit of how we write these models. This maybe is closely substitutable, but if you can always go at a higher level of disaggregation. Say the 6-digit level. If you look up at the classification here, you'll see these are plastic bags of ethylene and not of ethylene. So maybe that's like a more substantial distinction between these products. But this is what they're measuring here. They're measuring the counts of these things per firm. Now, I think the main question for this kind of measurement exercise is when we see a firm adding a product of this kind to its portfolio, do we actually know that it's improving its quality? Okay, and this is basically the same discussion that we've been having throughout this conference about the importance of quality adjustments in the context of the research on patents that, for instance, Ufuk has pioneered. This is similar to the problem of how do we adjust for quality in patents. Okay. I don't have a silver bullet here, but I think it's a problem that's worth thinking about as we go forward with this agenda. And there's some facts that Danial was showing us on this. I think it was in the draft, but they're really cool. One way we might be able to get at that is it the case that whenever a firm adds a product, it actually gains a substantial market share, like it's supposed to in these models? Maybe that reveals something about improvements in quality, but I think this is a nexus of questions that is very important. The other thing is this data is so wonderful you could ask other questions with it. And I don't know that this is for this paper, but one question I kept wondering about is which products are these guys adding? I mean, presumably they're adding products that are nearby what they already know how to do. That's not the assumption in many of these quality ladder models. Much innovation is undirected. You're kind of drawing at random from a unit line. But can we learn about this in the data? Does that put more constraints on the models we should be writing? I think that'd be really cool. The other thing is, again, not for this paper, but the spirit of the model and many models in this literature is that firms are foxes, to come back to the Zvi parallels here. They have to rely on product churn to survive, okay? So they have to explore different directions. I suppose in this data there are also hedgehogs. There are also firms that don't do much product innovation. Actually, actually 2/3 of the year firm observations in this data don't introduce new products. So it's not that frequent. And I just wonder what we can learn about these firms in that data. I have 2 minutes, so I'm going to be very quick on the model. My main point here was, so the novelty in the model exercise is to add these innovation bursts. And so naively, I thought what the paper was doing was take Kletekortum and add these innovation bursts. It turns out it's more complicated. And one reason it's more complicated, so this is the innovation bursts, as Danial had described, this kind of zeta distribution of the number of products you might draw conditional on successful innovation. Now, what I did, because I don't know I have time to waste, is I wrote that model where you just have innovation bursts plus Kletekortum and nothing else. The model Danial presented has more things. And it turns out that very simple model is essentially isomorphic to Kletekortum in a particular sense. And I'm going to have to skip some slides here, but the main intuition you should get for why it's isomorphic, it's because everything in Kletekortum is linear in the number of varieties. And so, for instance, this is the Bellman equation you would get in Kletekortum. If you add these product bursts, it looks exactly the same, except what I would call a marginal Q, so basically the continuing value conditional on innovation is scaled up by the number of products that you've added to your portfolio. So you can go through the math, and basically what you find, and I won't have time to show you everything, is that the rate of creative destruction is exactly the same as in the Clay-Quarton model, where you would modify certain parameters, basically the entry costs and the flow cost of innovation. You would rescale them, and it would give you the same equilibrium rate of creative destruction, therefore the same rate of growth. Okay. Now, what's awesome about their paper is that it can do more than Clay-Quarton, which is it can fit really well the firm size distribution. And in fact, I think there's a deeper thing here, which is that you can completely separate the firm size distribution implications of these models using the trick that they're coming up with from the aggregate growth implications. So they do get different implications for aggregate growth, and I think it's primarily because they introduce process innovation. But there's also other smaller things. Preferences are different. There's non-homogeneous costs of certain investments types in the model. So what I would suggest is try to keep it as clean as possible. Maybe just add process innovation relative to KK plus innovation burst, so that it's really clear that what's going on in this model, the reason why it has different aggregate growth implications, is the combination of the bursts of innovation with process innovation. Otherwise, you're back in the Clay-Quarton model. That's all I had, but it was a fantastic paper. Thanks a lot for having me.
Thank you very much.
Well, thank you so much, Nico, for this really thoughtful discussion. I'm going to very quickly try to respond to points, and I invite Martin if you have additional thoughts after I share my
but anything you say
so.
comes from time for you to get comments, so be quick.
Okay, of course, but I think it's important to respond to some of these points. So the first point, actually, it was very interesting looking at the differences between these products at the level of 10-digit. I agree with you that that might a little bit be too far going in terms of disaggregation. We look at these facts, as I mentioned, at the level of 8 and 6-digit as well, and the facts that we find are very robust with respect to those. I would mention another related point, which is that there is this other extreme that some of the literature on trying to look at the products has gone to, which is to look at barcode level data. Now, that's a different type of data because it doesn't cover a lot of the manufacturing sector that we can cover here. But that, if you go at that level, these distinctions are going to become a lot more pronounced in that some of the variations are really about the packaging being different. So there's some of that here, not quite as much. And again, if you do the aggregation, that the results are going to follow through. Another point that you made, again, really good point about are there quality improvements here? And I think our best attempt in addressing that point is to look at the graph that I showed you in terms of the revenue. It seems as if, on average, these firms are able to gain extra revenue by entering these markets. And so here, what we're doing is this dance between trying to stay close to the standard core models to facilitate the tractability, because once you mentioned some of the directions in which we can add richness to be able to fit more and more facts in the data, then and that's the direction that for sure we want to go. We think of this as more of an agenda and a single paper. But I think for this paper, what we want to do is to really stay very close to the core models. The point that you mentioned about Clay-Quarton, I'm going to use this opportunity to also mention a point related to that, which is you're absolutely right. You're absolutely right in the sense that if I were not to care about the concentration, if I were not to care about which firm owns which product, our model is not telling you anything new if you especially remove the process innovation part. But what we're trying to tell you is, in fact, as soon as you care about that, and there are many reasons for which you could care. In the standard Clay-Quarton model, there is no such ground, but in principle, we could come up with many reasons for which you would care. As soon as you care, then you have to bring in the facts that we're characterizing here, and that distinction, this isomorphism, completely breaks apart. So let me pause in that, and perhaps there are more points that we can discuss later and take some of the questions.
Quickly, we have about 5 minutes for some comments. Yes.